to introduce today, as part of our distinguished seminar series, Professor Guido Imbens, who is the Applied Econometrics Professor and the Professor of Economics at Stanford Graduate School of Business. Guido specializes in econometrics and in particular in methods for causal inference, and his work has had a great impact on a variety of areas, inclusively the area of machine learning and medicine. So it is especially wonderful to have him give this talk in our seminar series. Guido serves as an editor of Econometrica currently, and he's a fellow of the Econometric Society and the American Academy of Arts and Sciences. And he was also elected as a foreign member of the Royal Netherlands Academy of Arts and Sciences. He's also a fellow of the American Statistical Society. And it is really my great pleasure to have Guido give the talk today. And he will join us at the end for questions. Thank you. Navneet, Ami, who is going to play the video?
Yeah, just trying to figure out the screen share right now.
You may need to stop sharing the current slide and turn the other slide on.
Okay, it should be working now.
We cannot hear.
Okay, is it still no audio?
No, we cannot hear the video.
Okay.
Ami, I don't know whether you can make it work, but I was hoping that this was already sorted.
Yeah, it should have been working. Just give me a second. Okay, someone in the chat is saying that they can hear it, but at a very low volume. Okay, I'm just gonna stop sharing my screen for a second to figure this out.
Yeah, so thank you. Thank you everyone for bearing with us. Sorry for the technical glitches.
Okay, let's try this again.
Okay, thanks for inviting me to give this talk. I'm sorry I couldn't be there in person. Because I want to talk today about some joint work with Susan Athey and Raj Chetty on combining experimental and observational data to estimate treatment effects. And so kind of more specifically, I want to think about how we can combine experimental and observational data to answer questions that neither of them can directly, credibly answer. And kind of the hope is that methods for doing so will make experiments more valuable by extending the value of those experiments beyond the narrow questions that they were directly designed for. And in addition, we hope that methods for doing so will make observational studies more credible by grounding them kind of using experimental data, but the experimental data often give us very precise and credible answers for specific questions. And so I'm going to do this in two examples corresponding to two papers. First, I'm going to look at a paper where we have observational data that have relatively limited internal validity. We have observational data here that we're interested in the effect of class size on some final test scores. We have information on the class size, early test scores, and final test scores. And in addition, we have some experimental data that contains information on class size and early test scores, but not on final test scores. We see that the estimated effects for the two samples are very different. And so given that, we're concerned about the internal validity of the observational data, and we're not really sure that we can trust the estimates on the final test scores from the observational data. I will want to see how we can use the experimental data to improve the credibility of estimates on the final test scores. And in the second part of the presentation, I want to talk about surrogates, and that's kind of a literature that goes back a little longer. In the medical literature, there's a long-standing tradition of looking at surrogates as a way of allowing for short experiments. So if you're interested in the effect of some new cancer drug, instead of looking directly at the effect on mortality, which is really the object of primary interest, we can look at the effect on intermediate outcomes such as tumor size and use the fact that we think there's a positive relationship between tumor size and mortality, so that if we see an effect on tumor size, that is very, very promising for the possible effect on mortality. In the more modern settings, there's a lot of applications of a lot of interest in these ideas in the tech company world, where they often do a lot of short-term experiments where they measure a lot of intermediate outcomes. But what they're really interested in is some measure of long-term engagement with the website. And so they want to use all the intermediate outcomes to find some way of predicting what the long-term outcomes are, what the effects of the long-term outcomes are. And we'll show kind of some insights into the literature. And that work's also joined with Hyun-Sung Khan at University of Wisconsin. So to kind of set the stage here, let me look at some data kind of that I want to use to illustrate the first part of the presentation. So this is data by in this case, we're interested in the effect of small class size on 8th grade test scores. There was actually an experiment done to look at the effect of test scores of small class size called Project Schaar. And so here we have data from only for 3rd grade test scores. And we see that having a small class size, the treatment group, leads to considerably higher 3rd grade test scores. The effect is 0.201. Of course, I would say that's not particularly meaningful, but let's leave that aside for the moment. So there's a clearly very precisely estimated positive effect of having a small class size. Now, on the other hand, if we look at this observational data, which come from the New York school district, we see that the effect, even after adjusting for some pre-treatment variables, we see that the effect on 3rd grade test scores is negative, minus 0.138. And it's also negative for 8th grade test scores, minus 0.118. The question is really what to make of that. We have this direct estimate of minus 0.118, but in order to believe that effect, we also really have to believe the effect on 3rd grade test scores. And there it's given how different the the effect in New York is relative to that in Project Star, it's hard to really take the New York estimates very seriously. And as a result, we would also, be natural to question this estimate. So what can we do? But kind of to set up our approach, let me show some causal diagrams. What we're thinking of here is that in the observational data, we're interested in the effect of classroom size on 8th grade test scores. We think there's a direct causal effect, but we're concerned that there's an unobserved confounder. And the key assumption we're going to use is that whatever that unobserved confounder is, it also affects and compromises the direct analysis of the effect of classroom size on 3rd grade test scores in the observational data. So there's sort of going to be a key assumption, and that's not necessarily very well illustrated in the causal diagram, that this is the same observed confounder. Whatever goes on here is the same as what goes on here. And then in addition to these observed data, we have experimental data where we've eliminated the unobserved confounder by randomizing classroom size. But unfortunately, we don't see the 8th grade test scores there. We only see 3rd grade test scores there. So we can estimate this causal effect very well. And we're going to use the difference between these two to somehow adjust the estimate on 8th grade test scores. And kind of since the starting point is that this 8th grade test score number of minus 0.118, that's not credible. And the reason is we see this big difference between 0.201 and minus 0.138 that suggests there's something going wrong in New York, and that therefore the minus 0.118 is not credible either. And the question is kind of how can we leverage this difference between between these two to improve this estimate. And now, kind of a very naive thing to do, and that's not what we're going to do. At some level, you can think of what we're doing as some generalization of that. The sort of very naive thing to do would be to say, well, the bias in the 8th grade test scores is just the same as what it is in the 3rd grade test scores. So we see the bias in the 3rd grade test scores, the minus 0.138, minus 0.201, so about 0.34. And that's the same bias we would have seen in the 8th grade test scores. So we can eliminate that from the New York estimates. But clearly, that kind of simple adjustment is only going to work if the primary and secondary outcome are measured on the same scale. Now, in this case, they're both test scores, but it's still not quite. It's not quite clear they're measured on the same scale. It's also not quite clear what you would do if you had multiple secondary outcomes. Suppose we had both 3rd grade test scores and 4th grade test scores, or we had 3rd grade test scores in math and in English and in biology and in humanities or whatever. So here what we're doing is setting up a more general approach to dealing with the adjustment that allows for different scale and that allows for multiple secondary outcomes. And to kind of preview the results, what we're going to do is have a method that is going to transform this minus 0.138 into what we know is the ground truth, the 0.201, and then we apply that same adjustment method to the minus 0.118, and that's going to give us an estimate of 0.057. Now that's at least positive, so it looks now that small class sizes help the kids. But how do we know that's actually reasonable? Well, it turns out I lied to you earlier. We do actually have 8th grade test scores in Project Star. And so we actually know that the experimental estimate of small class size on 8th grade test scores is 0.085. And so this is actually quite close to our adjusted estimate that didn't use the 8th grade scores from Project Star. And so this is the way we're validating for this particular data set what we're doing here, that in this case, this adjustment method actually seems to work quite well, despite the fact that there's a lot of work to do. It has to actually move these estimates from minus 0.118 all the way to positive, but it gets quite close to what is arguably the ground truth there. So how are we going to do that, that's kind of what I want to talk about most of this this talk. But kind of let me start by setting up a little bit more formally what we're doing here. So we have a sample that consists of two parts. One, the experimental sample, Project Star part, where we observe for a number of units a treatment indicator and a secondary outcome and possibly some pre-treatment variables where we don't see the primary outcome. If we did, we would kind of be done. We would directly here be able to estimate the effect on the primary outcome. But for the second part of the data set, the observational New York part, we see all these variables, but we're worried that there's unobserved confounding there. In this particular setting, kind of where we see some of the outcomes in one sample and not in the other, it's also considered in some papers by Roseman and then Callas and Mao, but they make different assumptions, kind of focus on different estimates. They don't consider a setting where one of these samples is experimental and has great internal validity. So they look at different problems, but with the same data configuration. Now, to kind of set up continue with the notation, we have a group indicator that's in the GI that's either Project Star New York, the experimental observational sample. Then we have a treatment indicator, W, that's either 0 or 1. We have 8 grade potential outcomes for 8 grade scores, Y8, 0, Y8, 1. And then the same for the 3rd grade test scores, Y3, 0, Y3, 1. And what we're interested in is the average effect in New York of having a small class size on 8th grade test scores. But we think that simply doing some analysis on the New York data is not going to be good enough because of unobserved confounding. Now, what assumptions do we want to make here? So the first assumption is essentially definitional. We think of the observational sample as a random sample of the population of interest. Second, here is very plausible given the randomization. We assume that the experimental sample has internal validity. We get random assignment independence between the treatment indicator and the potential outcomes. The next assumption is the first kind of substantive assumption. We're assuming that the two populations are actually comparable. And this may be after adjusting for some pre-treatment variables. I've kind of left that out because that's not very interesting and it doesn't add any intuition. But we're assuming that fundamentally these two populations are the same. The problem and the reason why we get these different estimates, the minus 0.138 in New York and the 0.201 in Project Star, is because, and this assumption is saying that is because there's an unobserved confounder in New York, and it's not because the New York population is fundamentally different from the Project Star population. Again, we may want to do some adjustment for observed covariance to make them more plausible. But fundamentally, we're saying here, why are these two estimates different? It's because of the internal validity concerns in New York. It's not because the Project Star population is just so different, and in New York, small classes just don't really help at all. Now, what we don't want to do here, and I should really just cross this out, this assumption, what we don't want to do here is assume unconfoundedness in the observational sample, even given some covariance. We're concerned that fundamentally in New York, whether kids are in a small classroom or in a big classroom, is related to how well they would do in either of these regimes. If we made this assumption, then we wouldn't really need the experimental sample. We could just directly estimate everything on the observational sample, and given that that's actually larger than the experimental sample, there wouldn't really be much to gain from the experimental sample. If we're also making the conditional external validity assumption, we would be able to reject the full set of assumptions. So this is an assumption we're not going to make. But the problem is that just the conditional external validity in combination with the two earlier assumptions is not enough for identification of the average treatment effect. We need something more. And that one more thing is really kind of the contribution of the paper in terms of kind of novel identification results. We're making this assumption that we call latent unconfoundedness, that kind of for each of the two treatment groups, say for small class sizes, if we actually condition on what your third grade test score would be in a small classroom, whether you are in a small or big classroom is unrelated to your 8th grade test score in a small classroom. And this is kind of like an unconfounded assumption. We're saying, well, all the biases come from these from a set of variables. Typically, these are pre-treatment variables. Here, this is a particular potential outcome. But simply adjusting for that potential outcome, that's enough. That gets us, that removes the biases. And so another way of saying this, the assumption is that it's really that whatever the unobserved confounder is that leads to violations of this assumption, it's the same as the unobserved confounder that leads to violations of this assumption. And that's where the experimental sample is going to be helpful in allowing us to remove some of these biases. Now, the problem with this is that this is not a pre-treatment variable in the sense that it's not something we always observe for all units. So typically we would use pre-treatment variables to adjust for, but we can't do that with this variable. Even though we can estimate the conditional mean of 8th grade test scores in a small class size, given 3rd grade test scores in a small class size, in the small class size group. For adjusting, we also need to average this, we need to marginalize this conditional mean over 3rd grade test scores, and we don't know what this 3rd grade test score is for people in big class sizes. So we can't directly average this, we can't marginalize this out. And this is where the experimental sample comes in. From the experimental sample, we can get the marginal distribution of 3rd grade test scores in small class sizes, and we can do that adjustment. And so that kind of leads to this the main identification result. If we're making these 4 assumptions, so in addition to the latent unconfoundedness, we have this conditional external validity, and then these 2 relatively innocuous assumptions. If you make these 4 assumptions, then we can identify the average effect of the treatment on the primary outcome in the observational study. And so let's kind of look at the 3 estimation strategies for doing this. This is an identification result kind of doesn't have testable implications, so there's going to be a number of ways of estimating that in the end are all going to be first order equivalent, that can all be the basis of efficient estimators, even though they may not quite have the same properties in finite samples, but it's sort of 3 different strategies for getting there. And so one is kind of closely related to an older approach in econometrics called the control function approach, where we try to directly estimate the unobserved confounding variable. And the way we do that here is we estimate the conditional distribution function of 3rd grade test scores, conditional in in Project Star, in the experimental sample, conditional on the treatment group. And then we evaluate that for each observation. And by construction in the experimental sample, the control variable is going to have a uniform distribution. That's going to just, by construction, we estimated that conditional, well, we evaluate that conditional distribution function in a particular sample that's going to, by definition, have a uniform distribution. But it's not necessarily the case in the observational sample. If, in fact, it were to have a uniform distribution in the observational sample, then that would imply that there's no unobserved confounders. But in general, it's good to have a different distribution in the observational sample from the uniform one. And that deviation is going to capture the violation of unconfoundedness. And in fact, the latent unconfoundedness assumption implies that it captures all the violations of unconfoundedness. And all we're going to need to do to get rid of the biases is adjust for this control variable. So what we're going to do is we're going to first estimate that control function. We're going to estimate a conditional distribution function in the experimental sample. Then we evaluate that for all observations in the observational sample, and we're going to use that as a pre-treatment variable, exploiting the fact that by latent unconfoundedness, conditioning on the control variable makes the treatment assignment unconfounded with respect to the 8th grade test score. And so we can just incorporate this control variable in the analysis as if it is another pre-treatment variable that in fact we do observe for every for every unit in the observational sample. So that's kind of one way of thinking about it. Another way, it kind of makes a very different connection to the missing at random literature, kind of the Rubin Little type missing data literature. And so what we would do there is we would build a model that relates the primary outcome to the secondary outcome, the treatment indicator, and any pre-treatment variable. And we do that in the observational sample where we see all these variables. So we estimate a conditional distribution, and then we use that to impute, possibly multiple times, or kind of just whatever your favorite missing data method is. We impute the missing primary outcome for the experimental sample, and then once we've imputed that missing value, we just take the average outcome for the treated and subtract the average outcome for the controls in the experimental sample for the imputed primary outcome. And that gives us estimates of the average treatment effect there in the observational sample. Now, the third strategy there is kind of using weights. So we could think of the observational sample as having all the relevant information. It just has a problem with these unobserved confounders, and we can get rid of those by using weights in that observational sample, where we choose these weights so that the 3rd grade test scores in the observational sample weighted are equal to the average 3rd grade outcomes test scores in the experimental project Schaar sample. So we choose the weights to satisfy this equality, and then we estimate the average outcomes for 8th grade test scores in the observational sample using these same weights. So that kind of shows these 3 strategies for estimating the average effect of the treatment on the primary outcome in this setting where we have an observational sample that has all the relevant information, but that suffers from unobserved confounding, in combination with an experimental sample that doesn't have the relevant information, but it has great internal validity for the secondary outcome. Now let me move on to the second part. So here I want to look at surrogates. As I said before, kind of typically what in traditional medical surrogacy analysis people do is estimate the effect of a treatment on the surrogate, and then they combine it kind of with external knowledge of the relationship between the surrogate and the primary outcome. And that sort of sometimes has some complications. There's kind of this surrogacy paradox that you could have a positive effect of the treatment on the surrogate outcome and a positive correlation between the surrogate and the primary outcome, and it could still be that the average effect of the treatment on the primary outcome is actually negative. But here we can avoid some of these issues because we actually have data on the relationship between the surrogate and the primary outcome. We have a full data set, so we can estimate the full conditional distribution. And so compared to the previous setting, we now have, it's still the case that in the experimental sample, we don't see the primary outcome, but now in addition, we're missing the treatment indicator in the observational sample. The observational sample just consists of the observations on the primary outcome, secondary outcome, and possibly some pre-treatment variables. And so I'm going to mention two examples. One is, and that's the one I'm going to use some data from to illustrate these ideas. One is from the job training program, where we're interested in the effect of the training program on long-term employment. And surrogates here would be early labor market outcomes early on in the experiment. And sort of one practical question is, how long would we actually have to run these experiments to get a sense of the effect of the program on long-term outcomes? Because obviously, if you're interested in long-term outcomes, it would be very difficult to run the experiment for many years. And so in this particular case, we're going to look at an experiment where we're interested in outcomes over a 9-year period. And we want to see whether we could actually have estimated those effects credibly within a much shorter time period. And the second application, that's kind of where there's a lot of interest in these methods at the moment. Suppose in an online setting, we do a short-term experiment for about a month. We measure a lot of different outcomes, kind of how often people come back to the website, what ratings do they leave, how often did they buy something, how much did they spend in total, how long did they spend on each visit. But what we're really interested in is what is the effect of the treatment on the long-term spending, say 1 year spending. We want to estimate that in a month because we don't want to wait for an entire year. But so the example that I want to use to illustrate here is from the program from California in the late 80s, early 90s, called the GAIN program, Greater Avenues for Independence. So there was a program to help welfare recipients who are out of work to find work. And the Manpower Demonstration Research Company conducted a number of randomized experiments in 6 counties in California at that time. And so here we're looking at one of these 6 locations in Riverside. Riverside was a very interesting program because it was very effective early on. It was very good at getting people into jobs. And so partly that was because their focus was actually getting people into jobs. They didn't really do a lot of actual training, of classroom work. They just tried to help people kind of make calls, get through the interviews, and actually get into jobs. But the question was whether that actually helped in long term, or whether these were people just got into really bad jobs that didn't last very long. And so there was the important substantive question of what the long-term effect of that program was. And so here to illustrate that, if you look at the results for the experiment in Riverside in the first 6 quarters, you see there was a huge effect on employment. The average employment rate for the treated after 6 quarters was 30%, where it was only 18% for the control group, so a difference of 11 percentage points. The question is kind of what did that do if you look at average employment, so the fraction of quarters employed over a 36 quarter period, over a 9-year period. And so we're going to use this other data. In fact, this is also part of the GAIN data. So we just split the data in two. We use another part of the data to estimate the relationship between average employment over 36 quarters and the indicator for being employed in quarter 6 or not employed in quarter 6. And then we're using the combination of these two to figure out what actually would have happened had we followed the experiment for 36 quarters and seen what the outcomes would have been in the treatment and the control group. And in fact, here we do have data for 36 quarters, so we can see how well that works. It actually works quite well here. So kind of first, the overall employment rate after the 36 quarters here was 6.37%. So a substantial increase, but not quite as dramatic as what things looked like early on. The green diamonds tell you for each quarter what the average employment is over all the preceding quarters. So in quarter 6, it tells you that on average over the first 6 quarters, the effect was an increase in employment rate of 12%. And then you see that that slowly, and so you could use that as a simple kind of naive estimate of what the long-term effect is. You just look at the average over the first T periods. And you see that in order for that estimate to be close to the long-run average, you really need to run the experiment for a long, long time. But the preferred estimates, the surrogate estimates are the blue circles. They use the surrogate model to use all the data up to quarter T, say up to quarter 6, to predict, plus the relationship between the employment indicators for the first 6 quarters and overall employment over 36 quarters, to predict what the effect would have been over 36 quarters. And you see that after 6 quarters, that we can actually predict things pretty well in this case. This wasn't quite feasible with the data we have, because we're actually using the actual data to estimate the relationship there. But we see it works quite well here, even after 6 quarters, so even after a relatively short time, you can use the dynamics in the employment indicators for these first 6 quarters to predict that the overall effect is nowhere near the 12% that the naive estimates suggest. So how do we do that? So let me again kind of show a causal diagram to kind of see what the setup is here. In the observational data, we see the secondary outcome and we see the primary outcome. And we're assuming there's no unobserved confoundness there, so we can estimate that relationship accurately and validly. In the experimental data, we see the treatment and we see the secondary outcome, but we don't see the primary outcome. But we can estimate the relationship between the treatment and the secondary outcome accurately. And then we can combine these to estimate the overall effect. And so what we're ruling out, and so what is done typically in the mediation literature, is also allowing for a direct effect from the treatment on the primary outcome. We're ruling that out here, and we're assuming that that the only effect of the treatment on the primary outcome gets mediated through this secondary outcome. And this kind of exclusion restriction is very similar to what people use in instrumental variables analysis, where they also assume that particular causal effects only go through particular pathways and not others. So the traditional surrogacy assumptions are that we have that the treatment itself is unconfounded, and so we're going to assume the same here. Second, this is often referred to as the Prentice criterion. The surrogacy assumption is that conditional on the surrogates, the treatment indicator is independent of the realized primary outcome. That's kind of a tricky assumption. It's sort of a little hard to interpret from a causal perspective. And so what I want to do next is relate that a little bit to what is done in the mediation literature, and sort of make a little clear what the content of this assumption is. And then there's a third assumption that is often not articulated in the surrogacy literature, because people don't actually have the secondary sample, the observational sample. We're assuming that in the two samples, the conditional distribution of the primary outcome given surrogates and pretreatment variables is the same. And we'll see if that assumption is violated. There's also concerns. Now, in the mediation literature, things are set up slightly differently. There we start by assuming we're setting up potential outcomes that are indexed both by the treatments and the surrogates. We then also assume that the treatment is unconfounded, possibly conditional on some pretreatment variables. And we also assume that the surrogate is unconfounded, conditional on the initial treatment. But now, in addition to these mediation assumptions, we're assuming there's no direct effect of the treatment, that if we change the treatment but keep the surrogate the same, then the potential outcomes do not change. And we show in the paper that combining these three assumptions gives us implies the Prentice criterion that conditional on the surrogates, the treatment is independent of the realized outcome. So you can kind of think of the surrogacy assumption as really this combination of these three assumptions. Now, so next, I need to have some additional notation to kind of show what we can do under these assumptions. So there's kind of four objects here. There's the propensity score, which is the same as in the standard causal literature. We have something we call the surrogacy index that gives us the conditional expectation of the primary outcome given surrogates and covariates in the observational sample. And this is something we can estimate. In the observational sample, we directly see the primary outcome, we see the surrogates, we see the covariates, and so we can estimate this conditional expectation. Then there's also going to be a role for what we call the surrogate score. That's the conditional probability of having received a particular level of the treatment given the surrogates and the pre-treatment variables. So it's kind of a little bit like the propensity score, other than it conditions on an outcome that is potentially actually affected by the treatment. And so unlike the propensity score that would be constant in a randomized experiment, even in a randomized experiment, the surrogacy score is not going to be constant, because it as soon as there's an effect of the treatment on the surrogates, the surrogate score is going to vary by values of the surrogate. And the last thing we need is what we call the sampling score, that kind of measures the difference between the two samples in terms of the joint distribution of the surrogates and the pre-treatment variables. And we're going to need that to adjust for the differences between these two groups. And so, given these definitions, there's going to be three characterizations of the average treatment effect. First one is in terms of the propensity score and the surrogate index. And so we can, if we estimate on the observational sample the surrogate index, we can then average that in the experimental sample over the surrogates and the pre-treatment variables to get an estimate of the average treatment effect. Second representation depends on the surrogate score and as well as the sampling score and the propensity score. We can estimate the surrogate score in the experimental sample. We can estimate the sampling score, kind of combining the two samples, and then we can average this expression in the observational sample, where we see the primary outcome and all the other variables. And then the last representation, that sort of links things to the semi-parametric efficiency bound literature. We can calculate the influence function for the average treatment effect and use that to construct an estimator by plugging in estimates of the components of the influence function. And so that in this case depends on the surrogate index, on the propensity score, on the sampling score, as well as the surrogate score. And there's sort of some reasons to believe, kind of from the theoretical literature, that using the influence function is actually the preferred way that's going to have some, at least local robustness properties. Unlike the influence function in the standard unconfoundedness literature, this is not going to have the general global double robustness properties, but it still may have some local robustness properties. But so under the assumptions we're making before, all three of these are the same, and so they give us three different paths to estimating the average treatment effect. There's nothing we can do in terms of testing the assumptions by looking at the comparison between the two, irrespective of whether the assumptions hold. These are going to be estimating the same object, but they're estimating it in different ways, and so the finite sample properties may well be different. Now, it's kind of useful to look at what happens in a very simple case. Suppose there's no covariates. It's supposed to be we specify the surrogate index to be linear in the surrogates. Then the way you would estimate the average effect is kind of closely related to the very uncanny setup. We would estimate the average effect on the surrogates as S1 bar minus S0 bar, and then we would weight those, we would multiply those kind of with the relationship between the surrogates and the primary outcome. And this has been very helpful kind of in some of these tech company experiments, where suppose you're looking at an experiment where what you're interested in is the long-term engagement with the website, sort of measured over, say, a year. And now you have a bunch of different intermediate measures. How many times people visit the website, how long they spend on the website, how much they spend on the website. It's not quite clear how you should weight these different outcomes if you're trying to predict whether a particular intervention was successful or not. And the surrogacy approach kind of gives you a way of trading off these different outcomes using the systematic approach, namely kind of how they relate, how much they predict the primary outcome. And so it gives you an exchange rate between these different variables, that even in the absence of formal validity of the surrogacy assumption, even if there is some direct effect, it at least is going to give you some way of balancing these different outcomes. And so the final thing I want to say here is make some comments about what's going wrong if in fact the surrogacy or the comparability assumptions do not hold. And so if they don't hold, tau is not going to estimate the average effect we're interested in, but it is still going to estimate something. And so there's going to be two biases now, one bias coming from the violation of the surrogacy assumption and one bias coming from the violation of the comparability assumption. And you can see what the role is of the surrogacy score in that. In order for the bias from violations of surrogacy to be small, we need the surrogacy score to be close to 0 or 1. You need to be able to predict who's in the treatment group and the control group based on the surrogates very accurately. Then you don't have to worry so much about possibly direct effects of the treatment on the outcome, because the treatment is very well predicted by the surrogates. On the other hand, if we're concerned about violations of the comparability assumption, those violations lead to very small biases if the surrogacy score is close to the propensity score. If in fact the surrogacy score doesn't tell you much about who's treated or not. And so kind of if the surrogacy score is very predictive of the treatment, by violations of surrogacy don't matter quite as much. But if the surrogacy score is not predictive at all of the treatment, then violations of the comparability assumption don't matter quite as much. So let me then kind of end with some concluding remarks. So the principal kind of experiments are very good at what they do, but that's often a very narrow thing. Observational studies are also very good at what they do, but that's not necessarily answering the causal questions we're interested in. And so I think there's a lot of potential value in finding systematic ways of combining those data, where we leverage the strength of each of the type of data. And so here is kind of just two very special, arguably very special cases where there's actually where it seems like there's potentially considerable benefit to combining these. In particular, the surrogacy methods, kind of with multiple surrogates, are being used a fair amount now in some of the tech company experiments. So thanks very much, and let me then pause here.
So thank you very much, Guido, for this wonderful presentation. I think
Thanks for having me.
Thank you.
Good evening, everybody there. It's still early in the morning here, but
glad to be there. At least
so thank you. Thank you very much. I'm sure that questions are coming. So please, I would like to ask everyone who has a question, maybe either to raise your hand or to post it in the chat, and we will ask you to unmute yourself and ask the question. So please prepare your questions. But Guido, while I'm waiting for them to ask you questions, I'll ask you a very, maybe a question motivated by my own research. So we are doing quite a lot of research, not with the tech companies or with educational boards like you did, but rather with clinicians trying to build decision support systems to help them maybe decide in complex setting which treatment to use potentially for this particular patient. And one of the big challenges we face is, of course, that with these methods, the counterfactuals in general are not observable. So do you have any thoughts or any guidance for us, maybe coming from your interactions with other industries or more generally? What do you think is the best solution to provide clinicians not only with maybe recommendations of potential treatments, but other type of evidence? And maybe more generally, even how to validate this in the healthcare setting?
Yeah, I think the validation is very important. And so in the settings I've been focused on, sort of I've been working with people on these problems. So the issue is often that people want to make the decisions very quickly, and they want to, but they want to have evidence that whatever methods they're using work well. And so what we try to do is sort of occasionally do these much longer term experiments, and then try to apply these methods that use only the short-term outcomes in combination with other data sets, and see how well they work for these to replicate the long-term experiments. You saw that a little bit in the first part, kind of with these data from New York and Project Schaar. So it was very clear that just using the New York data wasn't going to give you very good estimates of what the effect was on the test scores in 8th grade. But given that we actually had the test scores from Project Schaar, we could see how well these methods replicated that. Because what we're actually ultimately interested in that case is what are the effects on the labor market outcomes later in life. Kind of do these early childhood programs or do small class sizes, do they actually matter not just for test scores, but for how well people do in the labor market subsequently? Because at that point, it is very hard to validate things completely, but you can validate a lot of steps along the way, and that in the end is giving us more confidence that these methods do help. But I think it's hugely important to kind of have these kind of somewhat special studies where you actually do have a good estimate of the truth and can use to validate these methods. In the econometrics literature, kind of one hugely influential paper was this paper in 1986 by Lalonde, where he had this randomized experiment, and then he put aside the control group from that experiment, and he used observational data to just see how well kind of the methods that people were using in econometrics in those days, how well they actually replicated the experimental results. And it turned out they did a terrible job. And that was hugely influential. That kind of led to Congress mandating experimental evaluations for a lot of these labor market programs, because they correctly viewed the state of the literature as being very unsatisfactory, that you couldn't really rely on these non-experimental methods. And now there's much more of a sense that whenever you come up with these new methods, you do need to validate them and really push them to see when they're actually likely to give you reasonable answers. And so a lot of the experiments I'm involved in are not just directly trying to get estimates, but also trying to just validate the non-experimental methods to get a better understanding of what's working there and what's not.
Thank you so much. Any questions?
Mihaela, I think there's no way to raise a hand. Can I ask a question directly?
Yes. Yes.
So thank you for the very interesting talk. I have questions about the latent unconfoundedness assumption.
Yeah.
So it seems like these assumptions requires we have outcomes over time, right? So if we have a similar settings in a static setting, suppose we don't have outcomes over time, could we make some similar assumption to combine experiment data and observational data?
Yes, so in principle, there's nothing that really relies on the outcomes being measured sequentially.
But in practice, it seems you need...
Yeah, in practice, that seems a very natural setting. And so, but suppose the observational data has two outcomes, they're both measured at the same time, you could still make the assumption that if from an experimental sample you have only one of the outcomes, that the unobserved confounders that drive the selection are the same in the two data sets. So there's nothing that would make it intrinsically not work. Another way of seeing that is that you can think of the latent unconfoundedness assumption in the end very much as a missing at random type assumption, and that doesn't require things to be sequentially have any sequential structure. So I haven't seen any good examples where you have two variables that are measured pretty much at the same time rather than the sequential nature. But it's certainly not the case that the two variables need to be the same type of variable. So in the example, it was third grade test scores and 8th grade test scores. But you could imagine that the primary outcome is labor market outcomes, say employment or earnings, and the short-term outcomes are a whole bunch of test scores, as well as what educational choices people made, what subjects they chose, all sorts of things that you could measure at an earlier stage to try to predict the labor market outcomes. And that's partly where Raj Chetty's interests were lying. He was he wanted to know what the effect was of these early childhood programs and interventions on labor market, on the things that we eventually care about, the labor market outcomes.
I guess the method still applies if we change the experimental data to observational data, and assuming the conditional unconfoundedness assumption holds, right?
Yeah, no, you're absolutely right. You don't really need the experimental data to be completely randomized. You just need to be able to estimate on those data fairly more credibly what the effect of the intervention is on the short-term outcomes, on the secondary outcomes. But if that data set is also observational but just has more credibility, then that would be fine. But partly the applications I was originally motivated by were settings where we did have these observational data that were very rich, but that clearly had a lot of problems, and we had these much smaller experimental data that we were really confident about, gave us the right answers, but not for the the right answers, not for the questions we were actually interested in.
And another thing I didn't see is in your analysis is the sample size. So, you know, when we look at this finite population central limit theorem of experimental data, the variance of the test statistics or estimator will actually depends on the sample size, right? So in your data, would you kind of rate the estimators in terms of sample size? You know, observational data, they have very high bias, but sample size is very large, the variance is very small. But experimental data, you kind of small samples and then have high variance. Do you think it's possible to kind of trade off the two?
Yes, so here in the two settings, I consider you can't, that's kind of difficult to do directly, because given the assumptions we're working with, in the end, the model is just identified. So you need the experimental data and the observational data. You can't, there's nothing left to play with anymore. So you could make stronger assumptions. So suppose that you make additional assumptions on unobserved confounders in observational data. At that point, you could get to a point where there's a trade-off between bias and variance, where you could put more or less weight on the experimental data. And that's kind of a direction some of the other papers in that literature have gone in, where you're actually trying to trade off those things, but there's enough information that in the end you can reject the absence of unobserved confounders. But given the latent unconfoundedness assumption, there's actually nothing testable in the data, so you can't get any mileage out of trying to balance those two here.
Yeah, we should let others ask questions as well, because you have an opportunity in the next meeting. No, anybody else that would like to ask any questions? So I think Sean has a question. Sean, would you like to unmute yourself?
Hello, thank you very much for the talk. Yeah, Sean Seaman. Excuse me if I'm asking you to repeat yourself, but could you clarify how your set of assumptions relates to a missing at random assumption?
Yes, so give me 1 second, and I'm going to try pull up. Just bear with me.
Navneet, you may need to allow sharing screen.
Yeah. Oh, yes. I'm going to need to do that in a second.
I've just done it. Sorry, I was on mute, but I think Amy's done it.
Okay, so I'm almost there.
It may be missing at random, Guido.
Yes, yeah, but
the slide.
Oh, so did I was. No, there was a particular slide, the slide that I didn't think is in here. Just bear with me one more. No, I can't find it now. So let me then go to this, just to the slides. Okay. So here for the surrogacy setup, it's a very classical missing at random setup. There's variable missing for some of the units, and everything is observed for everybody else. So you could just make a missing at random assumption that conditional on the treatment, the third grade outcomes, third grade test scores, and the pretreatment variables, the 8th grade the test score is missing at random. So there you can just the link is very clear. Now in the surrogate case, it's not quite so direct, because now there's two things missing. For the experimental data, the primary outcome is missing, and for the observational data, the treatment indicator is missing. But you can still make an missing at random type assumption, where conditional on the things that are always observed, whether you're in the experimental sample is independent of the treatment and independent of the primary outcome. So you get a joint independence that has very much a missing at random flavor. And kind of that the argument kind of allows you to kind of see that very directly that there's no testable implications of the assumption in that case.
Sorry, I didn't quite follow. So in the first setting, the assumptions you're making, that's it. The assumptions you're making are the same as missing at random or different?
They're not exactly the same, but they're consistent with missing at random, and they don't have any testable implications. So we're making assumptions on the potential outcomes. The missing at random assumption only makes assumptions on observed sort of on observable variables. But so here, missing at random would say that whether you're in the, if you think of this as just one data set, the indicator for being in the Project Star sample is independent of 8th grade test scores, conditional on everything else. Because here the missing data pattern is monotone in the Little and Rubin terminology. And so you could just, one way of approaching that then is to say, well, let's build a model for 8th grade test scores in observational data, given everything else, and use that to impute the missing values in the experimental data. And that is going to give you the same answers as our analysis. So you can show that kind of if everything is binary, then that's going to there's going to be a numerical equivalence.
Right. So so you're assuming something stronger than missing at random, are you?
Well, we're making assumptions on different objects. Okay, we're making assumptions here on the potential outcomes, and so the missing at random setup focuses only on the observed outcomes and makes an assumption on the 8th grade test scores, or the distribution of 8th grade test scores in the two samples. But the implications, the assumptions we make in the end imply that the data is missing at random. We make, in some sense, we make stronger assumptions, but the additional force of those assumptions has no content because it's about things we never see. It's only about the potential outcomes.
Oh, okay.
So Sean, maybe in view of time, I don't know, maybe a final remark, if you don't mind, and maybe we can wrap up and maybe the discussion can be continued in a subsequent email exchange or.
No, I'm happy. Thank you very much.
Sure.
Thank you very much, Guido, for the wonderful presentation, and thank you so much for visiting us virtually. And I think we saw people coming and listening to your talk from all sorts of departments. We never had such a diverse representation of people in Cambridge. So we hope that you are going to show to come and visit us in person soon, such that we can meet our own colleagues from many other departments interested on the topic due to you. So thank you very much.
Yes, I would love to visit sometime in person. It's been a long time since I've done any traveling, so
that is true. We hope to be solving this hopefully sooner rather than later. So thank you very much, Guido, for the wonderful presentation and all the discussions. And we will see you on some private meetings next. Thank you so much.
All right.
Thank you, everyone. Everybody. Thank you for joining us.
Bye.